Okay, good morning, everyone. So let's continue on with this chapter on potential energy. Let's just recap what we were doing last lecture. So let's start with this slide where we're talking about work done by an external force. So up to this point we were just talking about how you can exchange between, say, kinetic and potential energy, and the work was the energy that was transferred between the two. But of course some energy could actually come in from the outside and contribute to an overall gain or loss of the energy of some particular system. So this is an example here where a girl picks up a box. So in this case, originally the system might have, say, zero kinetic energy, zero potential energy. Then by somebody coming in and picking it up, basically it's putting energy into the system, right? So we can write this as something like this, where if we have some external force that's acting to basically give the system energy, then that energy that's flowing in will contribute to a gain or loss of the total of this kinetic energy and potential energy. So if you look at the kinetic energy before and after the process, then those things would have gone up or down by the amount that is either put in or taken out. So we can say that the external work is equal to the change in the mechanical energy in the system. So we can kind of visualize it like this. Previously we were just talking about work as being something that is between, say, the potential energy and kinetic energy, but actually if there's external work done on the system, then what can happen is that the overall energy of the system might increase, so that, you know, here the total energy of the system was, say, or total money in the system was $18. Over here it becomes like $26, right? So the total has gone up, and this is basically because this rich guy here has given this system a bunch of money, or energy in this case. So okay, this screen is frozen, so let me try this again. Now. Yep. Okay, or another example is if somebody is picking up a ball and then throwing it, so picking it up gives it potential energy, throwing it gives it kinetic energy, so of course there's an overall gain in the mechanical energy of the system. So we also considered an example where there was friction involved, and so in this case we kind of derive this from, well, basically the equations of motion of the system. So, for example, if you apply a force here and there's another frictional force pulling it backwards, then we have this is the total force, and then we've got Newton's laws here. This is just the equation of motion in one dimension. And then if we rearrange this equation where we rewrite, eliminate acceleration from the system, we end up with an equation like this. And basically this is telling you that the change in kinetic energy of the system is equal to, well, in this case, the external work done on the system, but less the energy that is going to contribute to friction. And friction eventually ends up as like thermal energy in the system. So basically the friction will cause the block and the table to heat up a little bit. So basically what we've kind of done here is that we've got kind of another type of energy, which is not just mechanical energy, but we've got thermal energy. And so you can think of it as kind of another bank account that you can have. So here we were just only talking about potential and kinetic energy, but thermal energy might be like a third bank account where you energy is going to be transferred between these three systems now, or three forms of energy. And then in the case of the block, basically this guy is your hand that's pushing the block, and that's going to contribute to increasing the bank account, the energy, total energy of the kinetic energy and the thermal energy. In this case, there's no potential energy change because the block is sliding just flat, right? But if it was pushed up a slope, then there would be also a potential energy change too. So this is basically a more generalized case of when there's not just two types of energy, but like three types of energy, and there's like thermal energy. So that's this example with friction. We did this one, and yeah, and I think this is where we got up to. I reshuffled the slides a bit, so I don't know if you might have looked at the slides that I uploaded on Brightspace, but I just reshuffled them around this morning, so this will appear in a slightly different order, and I changed one of the slides, so I can update the thing on Brightspace, slides on Brightspace later. So, so now we're going to talk about yet another type of energy. So we've talked about kinetic energy, potential energy. We just talked about thermal energy, but now we can also talk about internal energy. And basically, what is internal energy? Basically, it's the energy that might be stored, for example, due to chemical energy inside your body. So, for example, you have, of course, you have the ability to pick up and throw stuff, right? So that energy, where is it coming from? Obviously, it's come from the food that you ate, and the muscles in your body are ready to do work, right? And so what you're basically doing there is you are converting kind of chemical energy that is stored in your body and turning that into some, say, kinetic energy, right? So eventually it's all come from chemical reactions that are all happening inside your body, and that energy that's stored chemically is now converted into kinetic energy. So this is basically the kind of thing that we're talking about with internal energy. Doesn't necessarily have to be this sort of biological example that I just said. Perhaps that's the most tangible example, but it could be other types of chemical energy, or perhaps even say nuclear energy. So of course, if you have like an atomic bomb or something, then in that case you're converting kind of nuclear energy into, again, kinetic energy. Stuff is flying across everywhere. So all these things which are basically stored in some means where the energy is sort of stored in a kind of a medium that's got to do with the intrinsic constituents of what you're made up of, that you might call sort of internal energy. So so let's just have a look at an example of this internal energy transfer. So in this case, for example, if let's look at this example of a girl on ice skates, and as you can probably tell, all these slides are more or less following the textbook. But I found this example kind of quite confusing in a way. So it's good to kind of clarify some concepts on this. So let's compare the case of, so you have some girl on ice skates, and in the first case, say there's a guy and he just pushes her, she'll slide backwards. So this is an example of external work. So the system that we're considering here is the girl, and we consider this guy here the source of the sort of external work. Right? So in this case, the analysis is pretty straightforward. We can just apply whatever we learned before. And so we would say, okay, so the man is providing the external work. So say he pushes her through with some force through some distance. So he's going like this. And the force would be, of course, the force that his arms are providing. And then the distance would be like from here to here, right? So that's the work that you would work out that he's providing. Right? And so you would say that, okay, so that's the external work that's provided. Now, the kinetic energy gained would be equal to that work, right? So if she was initially at a standstill, she was initial kinetic energy 0, and then she goes backwards, she goes flying, the kinetic energy change is equal to force times distance. Okay, so straightforward, fair enough. Okay. But now let's look at a seemingly very similar case. Now say it's not the guy that is pushing her, but there's a wall here, and she pushes back on the wall herself, and then she goes backwards, of course. Okay, so superficially this looks kind of pretty similar, right? Okay, so in either case, fine, it's not a guy, it's a wall, right? So the wall is now providing force instead. We know that from Newton's third law that she's pushing on the wall, so the wall pushes back on her, right? Newton's third law, you know, each force is an equal and opposite force. So the reason why she goes backwards is because of Newton's third law, wall is providing force on her. Okay, so far it looks like, okay, fine, we've just replaced the guy with the wall, all right? But then if we do the same kind of analysis, we get into some kind of thing that looks like nonsense, because we might say, okay, well, instead of man, it's wall. And then we go, the wall is doing force times distance, okay, and the girl goes up by that kinetic energy. So this one is fine. But this one seems like it doesn't really make sense, because this would suggest that the wall is losing some amount of energy equals to force times distance. Yeah. So, and if you think about it, does the wall lose energy in this process? Or do you think the wall should lose energy? Yeah, no, right? So the wall is sort of just static, like it shouldn't be losing any energy. It shouldn't, you know. In the first case, yes, the man just did some work, so that he provided the energy. So he just gave the girl some energy, basically, right, by doing. In this case, it's pretty clear that the wall is not just like some source of energy that's like, it's going to push you. So there's something wrong with this analysis. So the kind of correct way to analyze this, and this is where you need this idea of the internal energy, right? So so the work done on the wall by the girl, right? So we basically, in this case, have to actually think of this other force, which basically in this analysis here we neglected really. So we were just looking at that force and then basically ignored that one. But in fact, actually, we should take that one into account because this is eventually where the energy is going to come from. Now, if you think about the direction of the force here, so this girl is applying a force on the wall, right? And she's pushing actually that way, in forward direction, in the opposite direction to the direction she's going to travel. So, because it's the opposite direction, actually this one will be minus Ft. So this will be a negative work. And this is the same thing that we just said on the previous slide, right? Okay. So this is the thing that's going to eventually contribute to the gain in kinetic energy. But what we basically didn't take into account on the previous slide is that this force of the provided by the girl is actually going to reduce the internal energy of her system, or her body, I guess, by minus Fd. And so in the end, what happens is that the internal energy plus kinetic energy, the sum of those two is equal to 0, as it should be, because essentially what's happening is that the internal energy in her body is going down, and the kinetic energy, itself is going up, right? So those two balance each other. So so we really kind of need this idea of internal energy, because otherwise we can't really, otherwise we get into something that looks like nonsense over here. So this is sort of the idea of internal energy, and essentially you can think of it as another bank account for energy. We've been looking at kinetic energy, potential energy. We looked at thermal energy, but actually we should also think about, say, internal energy, which is the energy that's coming from the inside, your body. For this example, another example is a car. So in this case, basically it's quite a similar situation to the girl on the ice skates pushing herself. So in a car, obviously, there's nothing that is pushing the car. The car drives itself, right? Obviously. So how do we think about this in terms of the energy transfer? Well, again, what you need to take into account are actually the two forces, not only the force that eventually drives the car forward, but also the car itself is actually pushing back in the backward direction. Right? So there are actually two forces here. This is the force on the ground by the car, right? That's going backwards. And according to Newton's third law, there's a force on the car from the ground going forwards, right? And those are in opposite directions, but then the car is going to go forward by d. So this means that this first one, which is the work on the ground by the car, this is going to be a negative quantity. And the second one, which is the thing that actually drives the car forward or gives the car kinetic energy eventually, is this is the work on the car by the ground. Right? The ground is actually pushing the car forward by force times distance. And this work, what that's actually eventually doing is changing the internal energy of the car. So in this case, it's not the chemicals in your muscles. This time, obviously, it's the petrol, gasoline that you are burning up in the car's engine, that chemical energy of the gasoline is being converted into kinetic energy. So, of course, you're burning that fuel. So that fuel, the internal energy in that fuel has now sort of gone down. So that internal energy goes down by minus Ft. Meanwhile, the kinetic energy goes up. Right? And again, the total of these two is equal to 0. It's basically the same example as the girl on the ice skate. Okay, so we can combine all these different types of energy. So, basically we've introduced 4 different types of energy here. We've got kinetic energy, potential energy, talk about thermal energy, and then now we just introduce internal energy. Right? So, essentially, when you look at a particular system, you need to, basically count all the different potential types of energy that the system can store that in, that basically will the total change in all these different forms of energy should be equal to the external work that you put in the system. Now, if you're thinking like, can you derive this internal energy change? I mean, I gave an example here, so it looked like it was basically the same. But in the end, what you really probably have to do to really measure the internal energy change here is to really, do chemical kind of analysis of, for example, in this car example, you have to say, okay, well, just sped the car up by this amount, and then let's look at how much fuel was burnt, and then let's calculate how much internal energy there is. So eventually, this is a kind of it's a sort of a fact of nature in a way, so that people did very careful measurements, measuring the change in energy of all these things, and found that basically this is always obeyed. So you can, if you carefully add up all the possible types of energy and then look at the energy changes before and after, then that should be equal to the energy that was originally put into the system. A special case of this is if the system is an isolated system. Isolated system basically means that no energy goes in or out. So basically this external work is 0. And so for an isolated system, what you'll find is that basically energy will just be transferred between these different forms. So you've got mechanical energy, that might go up or down, but then that eventually gets converted into, say, thermal or internal energy. So perhaps in some cases, usually the internal energy goes down and then it gets converted into some of these other things, but in principle there's no reason why it couldn't go the other way. So I changed this slide a bit because I thought actually this is a better way to think about it. So we can think of all these different forms of energy: potential, kinetic, internal, thermal, and again the work is just all these things, the energy transfer between these forms. Basically what this statement here is that if you say compared the energies in each of these after some process, if some, say, work goes into this system, then you should be able to figure out that, say, 3 joules went into this system. Then if you looked at the change in energy of all these different forms of energy, then it should be equal to 3 joules. That's basically what this is a statement that's making. Now, in the case that it's an isolated system, then no energy is going to go in or out. So any change here, it has to be balanced off by the change of something else. So, if this one goes up, then something over here must go down, right? So that it accounts for the fact that this has gone up. This is the example that they have in the book. So if you, this is perhaps a good example of a sort of an isolated system, right? So you've got a rock climber that is descending on a rope, and of course, if he lets go of the rope, he falls, right? So the rope is providing force upward. But if you think of it more from an energy perspective, then say he lets go of the rope a little bit, he's going to gain kinetic energy, and then he grabs onto the rope again. Then he slows, and then it actually stops again. And then if you think about where's that energy gone, well, so it's saying, where's my pointer? Okay, so he's wrapped the rope around the metal rings so that the rope drops against the rings. This allows most of the transferred energy to go to the thermal energy of the rope and rings rather than to its kinetic energy. So this is just an example of transfer between mechanical and thermal energy. Okay. It's frozen again. Right, and then finally, this concept of power, which was previously defined as the rate at which work was done by force. But we could equally generalize this to work as the rate at which energy is transferred by force from one type to another. So we've got all these different forms of energy, and then power is basically the rate of flow of energy, right? So some energy is going from one form to another, and that's happening in a particular time. So this energy change that's occurring between, say, E2, E3, if we look at the rate of change of the energy, of course, this energy might be going up, this one's going down, but that rate of change is basically equal to the power. We can either write it in this form if it's a constant process, or if this is changing with time, we can write it as sort of a differential. Okay. All right, so that's the end of that chapter. Any questions for that chapter? Yeah.
The T is the time.
Yeah, T is time here, yes. So, basically it would be like, say, this was transferring 2 joules in 2 seconds, then basically every second 1 joule is being transferred, so you would say that the power is 1 watt in that case. Okay, so if there's no questions, then we'll go on to this is the last chapter on this kinetic motion and things like that. I think after this we'll go on to thermodynamics. Okay, so this chapter is talking about momentum. So eventually we'll talk about conservation of momentum. Probably many of you have heard of this before, but it's also quite related to this idea of center of mass. In fact, they're kind of almost, well, they have a very kind of intimate relationship, if you like. So we're going to talk about center of mass first. So when we looked at projectile motion in the earlier chapters, we were always thinking of the thing as being just a point particle or a ball or something like that, and we never really talked about how the object might actually have some particular shape. Now, what if we're throwing something which is some weird-looking shape? Now, you can obviously imagine that the way that this will move is a lot more complicated in general. But there is a kind of way of thinking about it, or there's a special point where you don't have to actually think so much about the actual geometry of the object, and this is where this idea of center of mass is very useful. So let's just have a look at this video. Find the mouse. Okay, so they're throwing a bunch of things, and you can see that the objects have some fairly complicated motion, but if you put turn off the lights, and then this glowing dot here is the position of the center of mass of the object. And then you can see that actually, if you do that, then this actually behaves in a pretty simple way. So that wasn't center of mass. This one is center of mass. Okay, hold on. Let me just. Let's just look at it again, because it came on before I was quite ready. So, yeah, so you can see that basically, for a general object, basically, it doesn't really necessarily look like it goes in a smooth parabola, right? But if you only look at the center of mass, then actually it does. So these are the same objects, but then you just have the center of mass highlighted for this one. Yeah. So that looks like a perfect parabola, right? So of course it's still doing that same tumbling kind of motion that we saw before. So this one is just the regular center of the object. I think this is like some circular thing, but it's weighted on the side a bit so that it actually sort of wobbles. But if you actually put the dot in the center of mass, then it follows a smooth parabola. So let's go back. Okay, so there's a special point where there is a that you can actually eventually treat the object basically like a point particle. So it might be doing some, the other points of the object might be doing some more complicated motion. So for example, if you look at the tip of this bat here, so in this case it's actually looks pretty much like parabola, but if it was spinning more, then it might be sort of wobbling around as it's going around in this parabolic motion, right? So this is basically what we call the center of mass. It's a point that moves as though all of the system's mass were concentrated there, and all the external forces were applied there. So this is a really kind of neat way of basically simplifying the motion of objects, because if we didn't really have this, we would always have to think about like how this, this object is sort of tumbling, and then look at all the forces that are occurring separately, and then it would be a much more complicated problem. But then basically thanks to this concept, it saves a ton of work, right? Okay, so how do you work out where this special point is? This is the center of mass formula. So it looks like this, and then so you might think, what is this formula? Why is it like this? Basically, the way to think about it is that it's the weighted average of like the position. Right? So say you've got like two objects here, and one is say at this point, and another one is at this point, and they're separated by a distance d. Okay. Now, so you've got two objects, but then if say one is heavier than the other, M2 is say bigger than M1, just for this example, then because it should be a weighted average, you should kind of bias it a little bit more towards where this one is rather than where this one is. I shouldn't have touched the screen. Oh dear. Okay. Okay, yeah. So what you do is you basically, it's like doing an average, but then you put the mass of you put the mass as a kind of a coefficient on the position for each of the objects that you have. So you got M1, that's sort of your weighting factor, and then that's the position of M1. M2 is the weighting factor for the second object, and then you have to divide by the total mass so that you average over. So you get eventually something which has dimensions of position. And you might think that this sort of looks like it depends upon the coordinates, right? So this looks almost strange because for example here, let's say you took the origin here so that the coordinates of this one was 0, yeah? Then when you work this one out, you'd have that as 0, and then you'd only have this one. And then so that sort of looks almost wrong because it doesn't even take into account the position of position 1, right? And you think, how on earth could this work? Well, it actually still does work in the end, because eventually this whole thing is only really dependent upon the distance between the two objects. So even if you had a different convention for your axes, you'd actually still get the same center of mass here. This is the center of mass according to here. So shifting the axis will not actually, it doesn't really matter in terms of calculating the center of position. Of course, you have to be consistent in the way that you use your axes, right? So, for example, here, say this is like say 2 centimeters out from here, of course, the center of mass will still be 2 centimeters from here, but the answer that you'll get when you calculate the center of mass will be actually this distance, according to how you define your axes. So if this was 2 centimeters and this was 1 centimeter, then your center of mass, you get an answer 3 rather than 2 in this case. But physically, it's the same position. It's just that you're using different coordinates. Okay. Let's just just do a quick example here, just so that we can know how this works. So like center of mass formula is so who's got the keyboard person? Yes. I think you didn't press it yet. Should be on. Yeah. Okay, so that's the formula for the center of mass. And so, say we've got one object here and another object here, and then say the distance here is here. So we can look at a simple case where, let's just do a couple of simple examples of this. So let's look at the case when, say, if m1 is actually 0. So if m1 is actually 0, then there is no mass here, right? And where should the center of mass be for this case?
X.
Yes, exactly. Yeah, the position here. So the position x2. So if we just put that into formula, then m1 is 0, so it's going to be 0 plus m2 x2 divided by the 0 plus m2, and then we'll just get x2. So if this mass is 0, then the center of mass is going to be here. Now, if for the other way around, I think you can easily see that it's going to be the other position here. So if m2 is 0, then basically this is eventually going to give just x1, because that's 0, it's cancelled, it's exactly the same. Now, what if m1 and m2 were the same? Where do you expect the center of mass to be? Yeah, so by the way, this is, the center of mass, it's exactly the same thing as like the thing where if you try and balance something on here, right? So if you try and balance something here, basically what you're doing is you're putting your finger right under the center of mass. So I can't do it with this one, but if you have, in this case, if you go to like a stick or something, the center of mass would be basically the point where you can put your finger and then you can balance the stick on your finger, right? So in that case, where do you think it would be if these are like the same weight?
Middle.
Yeah, just right in the middle, right? Okay, so let's just check that actually works. So these ones are both m, and position of this one is, we can suppose it's we'll keep it to x1. M x2 and then m plus m. So this is 2m, and basically all these m's actually cancel. So you'll get x1 plus x2 over 2. So that's the middle of those two. Okay, so that's basically how center of mass works for 2 objects. Now, what if you had like more objects? What if you had 3 objects? You know, n objects. Basically, it's the same thing. You kind of weight them, and then you keep on adding all these things according to the weight, and then you have to divide by the total mass of the whole system. So you can calculate the position, center of mass position here. Now, basically, this kind of cancellation here in the mass basically always sort of occurs, if you like. So, you know, the dimensions of this thing, of course, it's a center of mass is a position, right? So the dimensions of this has to be something like meters or centimeters or something. So although you've got masses in here, because you've got the masses on the top and the bottom, any kind of units that you use will actually always cancel out. So, so actually you could just use grams or actually any units and it wouldn't really matter. So for n objects, you can generalize the center of mass like this. And this was for a one-dimensional case, but we could equally look at something in more dimensions. And in this case, what we just have to do here is to look at all the x, y, and z coordinates just separately. Okay? So for the x center of mass, it's just the x coordinates of all the different things. So this is saying sum over all the different masses that you have. So you sum all the different masses with this mi xi, and then this big M here, sorry I didn't define it, is just the total mass of the whole system. So it's the same as this denominator here. So we write it. M is the sum mi, which is equal to m1 plus m2 plus mn. And that will give you a three-dimensional, three coordinates to define the center of mass. So, okay, so that's, I did in 3 dimensions, but for 2 dimensions, this is an example like this. What you do here is you'd basically first look at the x coordinate. So here it would be something like, well, yeah, just work it out for this example. I don't have the numbers for M1, 2, but for that example that I have there on the slide, so the x center of mass, what you'd have is something like, so the first mass times the x coordinate, so that would be times 0. Second mass, what's the coordinate of x coordinate of the second mass? 2, right, 2. 2, whatever units. This one is 1. Divide that by m1 plus m2 plus m3. So that's just 0. So it'd be 2m2 plus m3 divided by m1 plus m2 plus m3. So that would be what you would have for the x coordinate. Maybe you have to press kind of hard. Yeah. Okay. All right. And for the y center of mass, you do something similar. So, you would get some coordinate here on the graph here. Okay, so that's for a bunch of masses. Now, suppose you had a continuous body. So how would you work this out? Now, this goes a little bit, I guess, beyond the course. I don't think I'm going to expect you to be able to do like a really complicated integral, for a very complex shape. So don't worry too much. But you should still know kind of how this works, at least for some simple examples. So. So essentially what you do is you extend this sum this time to an integral. Now, so we're going to look at, for example, some kind of complicated shape here. So say we have this semicircle rather, and we're trying to work out the center of mass of this. So what we're doing here is we're going to make an integral version of the same formula that we had before. So here we had x center of mass is equal to this. Now, when you turn sums into integrals, usually actually it's pretty straightforward in a way, because what you're basically doing here is kind of take your summation sign and then you just turn it into an integral more or less. So what you do have to be careful of is to figure out exactly like what is the small element that you are summing over. So in this case, essentially what you're doing here is something like this. So, for example, in this semisphere example, so here's our coordinates x and y, and if we just maybe stick to a two-dimensional example, so what we can do is to consider just like a tiny square on this thing. And of course we can chop up this whole thing into such tiny squares, right? And if we add up all the different contributions, so we know that the x center of mass, according to our formula, is equal to x sine my. So what we want to do here is we're basically chopping up the system into tiny pieces, and so the tiny piece that we have here, of course, will have some extremely small mass, right? Because we've chopped it up into such tiny pieces. Now the position here that's not tiny. That's just for example, in this case, that would be equal to that position there. Right? So the xi of this would be yi, and the mass of this thing would be mi, which, for example, if you were doing, the mass of this would be, it would depend upon how small you chopped your pieces up into, right? So, so the mi there would be that. So in this case, like the small piece that you're chopping the thing into would be mi. And okay, so we can write down basically what the mass of this thing here is. So it might be actually better to consider sort of like a plate like this, right? So that at least we have like a three-dimensional object. So we'll just say that maybe this is like T. And then So the mass of this thing would be like the density of the object multiplied by like the volume of this thing. And so when we turn this thing into an integral, basically what we do is we change the summation to an integral sign. This x is not a small quantity, so that's just stays as it is. And then we can convert this thing to, well, this thing is the small mass, so this is basically equal to the mass of the object. And then, so this is like your center of mass, but for a continuous system. Yeah.
Why is it density times the change in volume?
Well, it's not the change in the volume. It's like this would be like the small volume of this piece. Yeah. So because, for example, let's say you wanted to work out what the volume of this one here was, right? So it would be the width of this small piece here times by the width of this small piece in the y direction. And, well, okay, so if we're doing a general case, then it would be also the size of that thing in the z direction. So the small volume here, small volume would be equal to basically delta x, delta y, delta z. Because that's the small element that we're trying to, that we're going to be integrating over, summing over at this stage, but then eventually you take the limit as this whole thing becomes very small, and then that is actually equal to the volume. And so when you turn this into like an integral, basically you can literally just do something like this. This is actually if you were to do this sort of mathematically, then this would actually be a triple integral. So it would be actually like this, x, dx, dy, dz. And that's basically how you would work that out mathematically. I think it goes a little bit beyond this course. I don't think I'm going to ask you to do any triple integrals in the exam because I'm not sure if you've all learnt multiple integrals. Yeah. You have. I think maybe many of the class haven't. So yeah, I'm not going to ask you to do multiple integrals in the exam, but I mean, actually, it's actually not as hard as it looks just to have these multiple integrals. You basically just do the integral many times. So it's actually it's not as hard as it kind of looks, but I think you want to keep the idea of the concept of what you're doing here in mind. So, okay, yeah. So this is how you work out the center of mass for a continuous body. You basically do it by integration, and you are basically averaging over this variable x. In the y direction, it would be a y, and the z direction would be z. Okay. So maybe a slightly simpler example, just to start with. Would be to find the center of mass of this rod. So let me just sort of do this so that you might get a better feel for it. So okay, so we're going to try and find the center of mass for this rod here. In this case, we don't have to do the completely general thing that I was writing up there, because the shape kind of has a symmetry, so that we can take advantage of that, so we don't have to do a triple integral. We can actually just do a regular single integral. So what we're going to do here is we're going to slice up this rod into little plates like this. So this thing, what do we call it? So this dimensions of the rod are L and okay, and let's say that this this cross-sectional area is A, okay. And this, we've chopped it up into small pieces, so the width of that small piece is equal to delta x. Okay, so our center of mass formula says this. We're going to integrate x to, with respect to a small volume element, sorry, looks a bit different to whatever I had before. I think it's, oh, I see. Okay. Okay, so this is the density here, right? Okay. So just to first get this prefactor looking the same, so we can work out that the mass of this whole thing is equal to the density times its volume. Right? So that's the density, and then the volume is A times L, right? That's the volume of this rod at cross-sectional area A, length is L. So let's put that to here. So what we're going to get is rho divided by rho AL. These rows cancel. And then A times L is the volume of the thing. So this is basically what I'm starting off with. Now, the volume, what's the volume of this element here? The volume of this element is, well, that width times by the cross-sectional area. So that's the volume element, so I'm going to put that into there. So 1 over volume times x, and so I'm going to convert, sorry, I should put delta V here. So I'm going to convert that delta volume element into a differential. So we've got dx, and then the area here is just a constant, so I can pull that out and just write that over here. The limits of this integral, so I'm going to integrate it from the left, this left side to the length of the bar. So this integral is just 0 to L. So now that we've got it like this, now it looks like it's just, looks pretty easy. We can just integrate this thing. So let's go back and look the volume is area times length. So, and when we integrate this thing, it's half x squared, L0. These a's also cancel. So we're going to get 1 over L, and then if you just put in these limits, then it's half L squared, and that's going to be the L over 2. And that's exactly what you'd expect, because if you've got a uniform rod, you expect the center of mass to be just right in the middle. Yeah.
Wait, delta V and dV are the same thing.
Well, yeah. So when you do the integral, you kind of take the limit, right? So first, just in order to construct the integral in the first place, you can look at a small volume element. And at this point, it's just kind of small, but it's not like gone to zero yet. And then, I guess the standard procedure is that once you've written down the thing with the deltas, which is supposed to be something that's small but hasn't gone to zero yet, then you just change the delta to a d, and then it becomes like the limit of it going to zero. Yeah. Okay, so that's basically would be a simple example of calculating this thing. So we could avoid the triple integral in this case, basically because this thing just had the same cross section everywhere. So when we wrote down the small volume element, we only had to really kind of make it small in this direction. And then we didn't really have to do something like chop up this plate into tiny pieces along this way, because along this z-y plane here, basically everything is uniform. Within the integral, there's no variables that are like y or x or anything like that. So there's, we could sort of bypass that. But that's just because we had a relatively simple example. Okay. Okay, so, all right. So maybe just to finish up, we can try this question. So the question is to find the center of mass of this object here. Now, of course, you could do this kind of integral kind of way with this, but that would be pretty complicated. So basically, what you want to do is to try and figure out a way to sort of bypass doing the complex integral. And well, okay, so I think you can use the fact that for a circle, the center of mass should be just right in the middle, right? Okay, so you can use that as a given, so take that for granted. So, for example, if this hole wasn't here, the center of mass would be right in the middle. So, how about I give you a minute to think about how you might approach a question like this. Any ideas of how to bypass doing a triple or double integral? No? Okay. Shall I tell you the answer? Okay. Okay. So what you can try is doing something like this. So something like this is a bit of a complicated shape. So to work out the center of mass, we need something a little bit more symmetrical, right? So what symmetries do we know? Well, we know that, say, if we had a disk like this is the bit that's cut out, right? It's the missing part. Well, we know that that center of mass would be here, yes? We also would know that, say, if this hole wasn't there, the center of mass would be there, right? So we can actually use those two pieces of information to actually deduce what the center of mass would be for the thing with the missing part. And so we could do something like this. So first, consider this thing and say, if I've drawn that well. Okay. So this is so that's the x-axis. Say we start with the thing that's filled in, right? So say everything is filled in here. Okay. Then let's first work out the mass of something like this. So it would be, this is 2r, right? So the mass of this one would be equal to, so pi r squared, pi 2r squared. That's the area. And then, I don't know how thick this thing is, but, okay, so say we multiply it by that. Let's say the thickness is just, I don't know, T or something. Okay, so this would be the mass of the thing that's filled in. So it's 4 rho pi T r squared. Pi, yeah. Okay. And so that's the thing, the mass filled in, and then the position, center of mass position of that thing would be just equal to 0. Yeah. Now, so this is basically equal to the center of mass of the small plate. The mass of this one, so this has a radius r, right? So basically same thing except that it's 1r, not 2r, right? So you can see that this thing, the mass is going to be rho pi T r squared. And the center of mass of this thing, so maybe we can call it piece 1. This one is going to be minus r. So this is mass of piece 1. And basically, the combination of this one plus the thing with the hole that's missing Hi, can we do the keyboard?
Whiteboard.
Yeah, whiteboard. Yeah. This is the second piece. And what's the mass of this second piece going to be?
What's T?
We don't know what T is, but don't worry about it. Well, T is this thickness. Yeah. The thickness is the same for all these things. Okay, well, we're running out of time. So it's we know that this piece is missing from here, right? So we've got that one, that's that piece, and this one. So this has to be equal to 3 rho pi T r squared. And then this is the thing that we are trying to figure out. So we would call that x. Basically what we're going to do is we're going to combine these two pieces of information and then find the center of mass, but kind of over time. So I think I might continue this next lecture. But I think that gives you a pretty big hint if you're curious anyway. Okay.